Good morning. Today, I want to talk to you about one of the most important controllers, one of the most popular one, especially in industry, which is called PID control. Okay, so what we will do today is to learn how we can design a controller for our system such that it has a desirable behavior. Okay? Last time we talked about how we can specify what we want to get, what we expect from our system. And today we want to see how we can achieve those specifications by designing an appropriate controller. And in particular, we want to talk about a control technique, which is called PID control. And this is very popular technique. It is widely used in industry because of many reasons. For example, it has a very simple structure, and it can be understood by most of engineers without being an expert in control. And so working with it is very easy. And moreover, we are not required to have an accurate model of our process, our plant under control when we want to design a PID controller. Okay? So we want to talk about what is a PID control and how we can design a PID controller. PID stands for proportional derivative integral control, and so it has three parts: proportional controller, integral controller, and derivative controller. So for the first part, we look at the proportional control, and we look at what it is, what are the pros and cons of this type of controller, and why we would like to use it, and what it looks like, and so on and so forth. And so in the next part, we look at the next part of the PID, which is integral control. We look at what it looks like intuitively, what it does, and why we are interested in this type of controller, what are the advantages, what are the disadvantages. And finally, we look at the third part, that is integral control. And we study its properties, we analyze its properties and its effect on our control system, and we see what are the advantages and disadvantages of this specific controller. And finally, we put everything together with a PID controller and study its properties. Okay, and in the next part, we see how we can tune the gains, how we can design a PID controller. Okay, but I would like to show you a nice video before I get into detail about this topic. And this is prepared by some colleague of Professor Frazzoli at MIT, and it will give you some better intuition of what is this controller and how it works.
The technology being developed for driverless vehicles is pretty incredible. In the near future, there will be robotic cars traveling on normal roads with the safety and efficiency of the best human drivers. These autonomous vehicles use various sensors to be able to localize themselves in any environment. They are also then able to construct a detailed plan to get from their current location to any desired destination. This video will provide an introduction to how these autonomous vehicles are then able to follow their desired trajectories. Getting a vehicle to follow a trajectory may seem simple to those who have driven before, but is it? Let's take a deeper look at this in a lab setting. If we want to follow a line, but we are too far to the left, we turn to the right, and vice versa. But how much do we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bang-bang control. For controlling a car, this doesn't actually work that well. The response is very jerky and uncomfortable for the passengers. Fortunately, we don't have to steer like this in a car, since there is a range of angles the steering wheel can take. One way to set the steering wheel angle is to use what is called proportional control. Rather than turn the wheel a fixed amount, proportional control steers harder the further away we are from the desired trajectory. We take a measurement called the cross-track error to define how far away from the desired trajectory the vehicle is. Therefore, the steering angle we use is this cross-track error multiplied by a scaling factor called the proportional gain. The range of values the proportional gain can take drastically alters the performance of the vehicle. As you can see from this overlay, the performance gets better as the gain increases, but at a cost. If you start too far away from the desired trajectory with a high gain, the system can spin out of control. With the best gains, proportional control returns better results than bang-bang control, but it still doesn't work that well. With proportional control, the car can be crooked when it reaches the center line. The result of this is that the controller will repeatedly overshoot the actual desired trajectory and not actually follow it. To correct this overshooting problem, we need to consider additional error measurements and use them to update our steering command. A good candidate for an extra measurement is to look at the cross-track error rate, or in other words, how fast we are moving in a perpendicular direction with respect to the desired trajectory. If we are perfectly following the trajectory, our cross-track error rate will be 0. In control theory, this is what is called a derivative term. This rate term can then be multiplied by its own gain and added to the proportional term to construct an updated controller. Now that we have two terms, we have two gains that must be tuned simultaneously. Conceptually, we can think that increasing the proportional gain will increase the pull that the vehicle feels towards the desired trajectory. Increasing the derivative gain increases the resistance the car will feel against moving too quickly towards the line. Fixing the proportional gain, if the derivative gain is too low, the system will be what is called underdamped and it will still oscillate. If the derivative gain is too high, the system will be what is called overdamped and will take a long time to correct for offsets. Properly choosing the derivative gain allows the car to approach the desired trajectory quickly with a cross-track error rate close to 0. This is called being critically damped. Despite the success so far, for a complete controller, we're not done yet. Environmental factors or mechanical defects can change the vehicle's nominal behavior and thus the performance of the controller. For example, if there's a heavy crosswind, the vehicle will drift unless the driver counteracts this wind force with a corrective steering command. Here is an example we can easily demonstrate. Imagine our vehicle is driving along and hits a pile of rocks, which knocks its front end out of alignment, and therefore a 0 steering command no longer keeps the vehicle driving straight. As you can see, with the controller that has been described so far, the vehicle experiences a buildup of a lane offset, or a steady-state error. One way to address this problem is to add yet another term called an integral term. This third measurement sums up the cross-track error to give an indication if we are spending more time on one side of the trajectory or the other. You can see that if we sum up the cross-track errors, we obviously spend more time on one side of the trajectory. The integral term we propose is then exactly this sum multiplied by a gain. Now, 3 gains will need to be tuned all at once, which can be quite difficult to do by hand. If the gain is too large, the controller can go unstable because normal controller fluctuations will be exaggerated. If the gain is too small, it can take too long to respond to these dynamic changes. When the gain is just right, the controller will be able to quickly correct for the front-end misalignment and return to its nominal performance. The combination of these 3 terms is then what is referred to in control theory as PID control. There are other more advanced controllers that can be used for self-driving cars, but they will all look similar to the one we have described in this video. There will always be some measurements made about the state of the vehicle which are then compared to some desired vehicle trajectory to construct a steering angle that ultimately controls the car. Hopefully this gives some insight into the control strategies that can help make self-driving cars possible.
So, okay, as I mentioned last time, we talked about how we can specify what we expect our system, how we expect our system to behave, and we interpret the specifications in terms of some of the properties of our plan. For example, some of the properties of its transfer function, its dominant poles, its body plot, its root locus. And for example, one of the most important properties that we expect from our system is that we want the output of the closed loop system, the response of the closed loop system, track the reference signal. So we have a system like this, a controller that we design, and we close the loop like this. Okay? And this is the reference signal, R of t. This is a negative feedback. And this is the output, the response of our system. And we want our output of the system to track the reference signal which has the desired value. So we want the error of the system, which is E of t is equal to R of t minus Y of t. We want to have a zero steady state error, okay? So how we can specify this property, this expectation? We can say that it is translated into the number of integrators in the loop transfer function, in the forward path, okay? So, and the number of integrator in the loop transfer function is called the type of the system, okay? These integrators should be either included in the transfer function of our plant in L of S, or otherwise we should provide these integrators, the sufficient number of integrators, in the transfer function of the controller C of S that we want to design, okay? The other specifications, some of them are described in time domains, including, for example, the maximum overshoot, the settling time, the rise time, that determines the speed of the response of the system, so on and so forth. And they can be translated into the location of the dominant poles of the closed loop system, okay? So we care about, for example, we have two dominant complex poles like this, okay? We care about the real part of the dominant poles, which is this, and it specifies the speed of the system, so that if our pole is far away from the imaginary axis, then we can say that our system is faster, our response is faster. And we also care about the damping ratio. So consider this line from the origin to the pole, okay? And the angle, consider the angle of this line, say theta. And you can say that the damping ratio is that cosine of theta, okay? So the damping ratio determines the shape of the response and determines the oscillation in our response, okay? And we can examine these time domain specifications by looking at the root locus of the system. Okay, more important in some sense is frequency domain specification, like command tracking, or the disturbance, or the noise rejection, or the closed loop bandwidth of the system, okay? And these are translated into some obstacles on the body plot. And we want our body plot to keep away from these obstacles to achieve these specifications. Right? Okay. So these are the specifications of our system. These are our expectations, which are expressed in terms of some mathematical properties, some related properties of the system. But now the question is that how we can achieve, how we can get these specifications, these objectives. Okay. There are some methods to design controllers for our feedback system so that it behaves well and the specifications are met. There are many approaches introduced in the control textbooks and control references, like, for example, PID, loop shaping, LQR, LQG, LTR, H-infinite controller, discrete time optimal control, continuous time optimal control, or MPC, that is model predictive control, okay? But today we want to look at one of the most widely used, one of the most popular approach that works for many cases, especially for the CISO system. And we can say that something around 95% of the whole control systems that we know today are PID. And this is because of the advantages of this simple controller. It has a very simple structure, but it is very powerful. It works in many cases. And we don't need to have an accurate model of our system, and we can design a PID control for it, and so finally it works well. Okay. Let's look at the first part of the PID, which is the proportional control. Okay. But first, let's look at the standard setup. The block diagram of our closed-loop system is something like this. And we have a plant. We choose a plant, a very simple plant here, which is a first-order plant. It is 1 over S plus 1. And you see that this is a plant that has only one pole, which is stable. So the system is openly stable. And the pole has to be on the real axis because we have only one single pole. And it is on the negative part of the real axis. So, we can say that it's stable. So everything is very easy with this plant. It is a very, everything is very clear. For example, we can draw the body plot of this plant very easily. You know that the body plot is something like this. The magnitude plot is, we start with a flat line, okay? And then at the frequency 1, okay? We go down at a slope of minus 20 dB per decade. And what is the phase plot? We say that we start with 0 degrees, okay? And 1 decade after the pole, we converge to minus 90. Degrees, and we have a linear behavior in between. Okay? So this is the body plot of our plant. And okay, so this is a plant, this is a transfer function with an input and an output. Okay? And then we measure the output and we compare it, with the reference signal here. And we are adding a reference signal, which is a unit step. It is a unit step which has a unit value, okay? So we compare the reference signal with the output. The difference between these two signals is our error signal, okay? And then we use a proportional control here, which is just a gain, a static gain. And in this case, it is 5, okay? So it is a gain that converts the error, which is of the dimension of the output of the system, into the control input, which is of the dimension of the input of the system. Okay, so it's dimensionally the ratio of the input dimension over the output, the input dimension over the output dimension. Okay. And then we are adding a disturbance here. What is the disturbance? The disturbance is everything that comes from the outside of the plant, and it is exogenous. It is an external signal. Sorry. Okay. So we have a reference signal, which is a step at time 0. And then after 5 seconds, we consider a disturbance that is applied at the input of the plant. And you should note that there are 2 scenarios for the location of the disturbance. We can have it applied at the input of the plant, or we can have a disturbance at the output of the plant, like this. But which one of them makes more sense? We can say that the first one at the input makes more sense, because the disturbance changes the behavior, changes the way that our system behaves, not only the value of the output. Okay, so we consider the disturbance here, but when you want to find the transfer function from the disturbance to the output of the system, you should note that the transfer function in these 2 cases are different. Okay, right? So, for example, you can consider a room that we want to control its temperature. Okay, the outside of the room is cold, and we want to have a good temperature for the inside of the room. We have a heater in the room, inside the room, and so we switch it up, and we control the temperature. Okay, but what is the disturbance here? What can be considered as a disturbance for the temperature control of the room? For example, we can say that we have some windows and door in the room, and so if we open or close the windows, it can be considered as a disturbance that is applied at our system. Okay, and it can change it can affect the response of the system. It can affect the temperature of our room, because there is a heat transfer between inside and outside of the room, and so we have a heat transfer from the inside of the room to the outside. Okay, and so we want to reject the effect of the disturbance. We want to design a controller such that reject the effect of this external signal that we don't have any control to it. Okay. The other thing that we are adding here is a noise. Here, okay? What is the noise? The noise is everything that we get at measurements. We said that we want to measure the output, and then we want to compare it to the reference. So we need to have a measurement, and you should note that we cannot have a perfect measurement ever. And so we always have some errors when measuring something. And this error, we know that the output is a signal over time, and so we measure it continuously, and so the error in measuring the output of the signal is a signal as well. Okay, it is a signal over time, and so it can be modeled as a random signal. Okay, and it is, for example, we can use a white noise to model the measurement noise of our system. And so we want to see what is the effect of the noise on the behavior, on the response of this closed loop system when we use different controllers. Okay. So here we have just a proportional control. And now I want to show you some response of our system, some of the output of our system for different values of the proportional gain. For example, here K is equal to 2 Kp. Here Kp is equal to 5. Here Kp is equal to 10. And here K is equal to 50. Okay? So we want to increase the gain, the proportional gain, and we want to see what happens to the response to the output of the system in the time domain. Okay? So the first thing that you may notice is that our closed loop systems for every value of the k, for whatever value of the k, remains stable. Our reference signal, you see that it was a unit step, so it's something like this. This is the reference signal, okay? And it is bounded. And you see for all of these cases, our output of the system is bounded as well. So the system remains bounded input, bounded output, stable, okay? And the other thing that you may notice, that you may observe, is that the steady state error of the system decreases as we make the proportional gain higher and higher. What is the steady state error? This is the difference between the reference signal and the steady state value of the output of the system. So we should look at the value of the output here. I should mention that we have a disturbance here, and so we come down in the output of in the response of our system, okay? So this is the steady state value of our output. And so this difference is called the steady state error. And you see that when I increase the gain, the steady state error decreases. Okay? The other thing that we may notice is that you see that the response of our system would be faster when we increase the gain. Okay? And this is clear when you look at the response of the system in the time domain. And moreover, you can see that the sensitivity to noise increases. You can see the effect of the noise much more substantially here for Kp equals to 50. But when Kp is equal to 2, the effect of the noise is the sensitivity of the system to noise is very low, right? Okay. So, I want to say that we can look at the effect of the proportional control, every controller that we introduce from different aspects by using different tools. For example, here we used and we looked at the time domain response of the system, but we can look at the response of the system in the frequency domain, and we can use also the other tools like root locus, right, Bode plus, even Nyquist plus, and these are different ways of looking at the same thing. Okay, and we emphasize different aspects by using different tools. Okay, so now we want to see what happens to the root locus of this system. Okay, what is the root locus? What does it look like? You see that our loop transfer function is k over s plus 1. Okay, so we have only one pole at one open loop pole at -1. Okay, and so the root locus is some part of the real axis like this. Okay, so for low gain, for low proportional gain, we start from the open loop pole, and then we move to left as the proportional gain increases. Okay. So we can see that the real part of the closed loop pole would be larger when we increase the proportional gain, and it means that the response of the system would be faster. Okay? So we can compute the closed loop pole very easily for this simple plant, and we say that the transfer function, sorry, it should be k. Okay. The transfer function between the reference signal and the output signal is k L of s over 1 plus k L of s. And so for this case, we can say that it is k over s plus 1 plus k. And so you see that the pole of the system would be the root of the denominator, which is minus 1 minus k. Okay, so you see that if I increase kp, the proportional gain, the closed loop pole moves to the left to go to the infinity, and it would be more stable, okay, and faster. What can we say about the steady state error here? To compute the steady state error to the unit ramp, you should note that we can consider the unit step as a sinusoid with a zero frequency, and so we can write it as e to the power 0 times t. Okay. And so this is a sinusoid, this is an exponential, and we can find the steady state value of the output of the system at the same frequency. So we should set s to the 0, and we should find this limit here. Okay. So ESS, the steady state error, would be here for computing the steady state error. Notice that we should find the transfer function between the error signal and between the reference signal and the error. Okay, not the transfer function between the reference and the output. Okay, so this transfer function is 1 plus 1 plus k, 1 over 1 plus k L of s, which is s, sorry. Okay, which is s plus 1 over s plus 1 plus k, and when we set s to 0, then we obtain 1 over 1 plus k, and so this is the steady state error. Okay. So notice that our steady state error is a finite value, okay, but it cannot get to 0 ever, okay. We can make it smaller and smaller if I choose a larger proportional gain, but I cannot get it to exactly 0, okay. So why the error in the proportional control cannot be 0? Let's see again the block diagram of our closed loop system. You see that we have a transfer function. It has an output, it has an input, and we want our output to track the reference signal to reach a specific value, a desired value. So we should provide an input for our system so that its output has the desirable behavior, okay? So the input of our system should not be 0, okay? But if our error signal is 0, and when we multiply it by a proportional gain, then we provide a 0 signal here, if it is 0, okay? And this is not what we want to have, okay? So because we want to have a non-zero input, our error has to be non-zero, okay? So we just can make the steady state error smaller and smaller, but we can't make it 0. We can't have a 0 steady state error for the proportional controller. Okay, let's see what happens on the body plot of the system. What is the effect of the proportional control here? You see that the only effect of the proportional control is that it shifts the magnitude plot up, okay? And it doesn't have any effect on the phase plot, right? Okay. So this is for k equals to 2. Here k is equal to 5. The yellow line is for k equals to 10. And this is for k is equal to 50. Okay? So what happens to the crossover frequency and the phase margin of the system here? What is the crossover frequency? For computing the crossover frequency, you should consider it as the frequency where the magnitude plot of the response of the system crosses the 0 dB line. This is the 0 dB line. So you see that this magnitude plot for k equals to crosses here, and this one crosses at this point, and this point. So these are the crossover frequencies of different plants, for different proportional gains. Okay? So what is the phase margin? For computing, in order to compute the phase margin of the system, we consider the crossover frequency, and we see what is the difference from the phase of our plant to the minus 180 degrees. Let's say minus 180 degrees is somewhere here. Okay? So this is the crossover frequency, and you see that the phase of our plant, this plant for k equals to 2, is this one. And so the difference from this point to minus 180 is this, which is the phase margin here, okay? And for the other crossover frequencies, for the other plants, we have these phase margins. So this is for k equals to 2, 5, 10, and 50. So you see here that the phase margin of our system decreases, but it is quite large in all of the cases. It is more than 90 degrees, which is plenty, and it shows that for the case of a first order plant, this is just for the first order plant, not the higher order plant. Okay, for the case of the first order plant, for whatever value of the proportional gain, our phase margin is more than 90 degrees. And it shows that our closed loop system is not only stable, but is also robustly stable, okay? So it is a good thing. And what else? You see that the crossover frequency here increases by increasing the proportional gain. And it can be good in some sense. It shows that our system would be more informative, okay? But one of the bad effects of this is the effect of the noise on our system, on our response, okay? What is the frequency of the noise? The noise is a signal with high frequency. For example, it appears from 100 hertz. It appears from, let's say, here, okay? And this is the region that we have noise. Okay? So you see that as I increase the proportional gain, the bandwidth of the system and the crossover frequency of the system increases. And so we can say that our system would be more sensitive to noise. Why? For example, for this case, for k equals to 50, we amplify the noise. The amount by which we amplify the noise is this, which is larger, which is 10 times larger than the amount by which we amplify the noise for this plant, okay? So we see the effect of the noise in our response more substantially when we use a higher proportional gain, okay? And the other things that you can observe is that both low frequency gain, the gain at low frequencies, and high frequency gain, you can see both of them increase, okay, as we increase the proportional gain. Okay, so for the proportional control, for the first part of the PID control, we learned that we cannot make a zero steady state error. We cannot have a zero steady state error. We just can make it smaller and smaller by choosing a higher gain, okay? And we cannot get it to exactly zero. So, but when we choose a higher gain, the bad effect is that our system would be more sensitive to noise, okay? So there is a trade-off here that we should solve it so that our system is less sensitive to noise while the steady state error would be very small or would be close to zero, okay? For solving this problem, we can introduce an integrator, okay? In fact, using an integrator can increase the type of our system because we said that the type of the system is the number of integrator in the loop transfer function. And so if we design a controller that has an integrator in its transfer function, then we can increase the type of the system, okay? And for a unit step, we can put only one integrator in our loop transfer function, okay? But for higher order ramp, we should put more integrators, okay? If we have a ramp of order n, we have to put n plus one integrators in our loop transfer function so that the steady state error is zero, okay? So here we add a term, we add an integral term so that we can have a zero steady state error. So we take the error and we multiply it by a proportional gain here, okay, which is called Kp, which is denoted by Kp. And then we take the error, we integrate it, and then we multiply it by a proportional, an integral gain, which is denoted by Ki, okay? So we can say that the control input, which is the output of our controller, this is our controller, our proportional integral controller, okay? The input of the controller is the error, E of t, and its output is called U of t, okay? So the control input, which is the output of our PI controller, can be described by this form. It is a proportional gain multiplied by the error plus an integral gain multiplied by the integral of our error over time, okay? So consider this term. If the error is oscillating, then we can say that this integral can be zero, and we can ignore this term. But if it is only in one direction, okay, let's continue after the break. Okay, take a seat, please. Let's get back to the lecture. Okay, so we showed that the control input in the time domain can be represented by this formula. And so we take the error, we multiply it by some proportional gain, and in parallel, we take the error and integrate it, and multiply it by some integral gain, and then we add these two terms together, okay? And we said that if the error is only in one direction, then this term starts growing, and we cannot ignore that. So in the PI controller, it accumulates the error, and so it considers the error over time. And so in this case, we can have a zero error, okay? And what can we say about the representation of the controller in the frequency domain? We can say that the transfer function of our controller is something like this. We have these two things in parallel, these two transfer functions in parallel, and so it would be Kp plus Ki over S, okay? And we can write it as the body form, like this, okay? So this is the body gain. The body gain here is Ki, and this is a transfer function. This has a nominator, this has a denominator, so it has a pole. You can see that it has a pole at the origin, and it has a zero at minus Ki over Kp, the zero of PI controller. Okay? So this is a transfer function. So this compensator, the PI compensator, you see that it has a dynamics, okay? Unlike the proportional control, which was just a gain, a static gain, we have dynamics here. We have zeros and poles and the transfer function here, okay? So let's look at what happens on the response of the system when we use an integral action, a PI controller. And here we keep the proportional gain to a constant, to a fixed value. We keep it to 2. And you can remember that for proportional control, if Kp was 2, the steady state error was large, but the system was not sensitive to noise, okay? So we keep it to 2, and we change the value of the integral gain. We increase the integral gain, for example, here, here. The integral gain Ki is equal to 2. It is for Ki equals to 5, Ki equals to 10. Sorry, it should be 5 and 10. And this is for Ki equals to 50. Okay. So in this case, you can see that for all of these cases, the steady state error of the system becomes 0. This is the reference signal. It has a unit value. And you see that the steady state error would be 0, okay? And the other thing that you may notice here is that as we increase the integral gain, the response of our system becomes faster, but it becomes more oscillatory. We can observe more oscillations when we increase the integral gain, okay? So in control, when you have lots of oscillations, you should note that it is a warning, it is a bad thing, and it means that your system becomes close to be unstable. Okay, and it means that the damping ratio of your system is reduced. Okay, so one of the effects of a PI controller is that it decreases the damping ratio of the system, and it increases the oscillation of the system. It makes the response of the system more oscillatory. Okay. The other thing that we may observe is that, as I said before, the speed of the system is faster here. So you can see that for the higher gain, the effect of the disturbance, we have the disturbance here, the effect of the disturbance is rejected quicker. Okay? And the side effect, the bad side effect of using the integral gain is that, here, the sensitivity to noise doesn't change. Okay, and we can look it by we can see it by looking at the body plot. Okay. So. Let's look at the same thing from the other viewpoint. And we want to see what happens on the root locus of this system. Okay, let's see. So this is our plant. Okay. And this is the PI controller, which is Kp plus Ki over S. And we close the loop like this by negative feedback. Okay. So we can say that the loop transfer function is a product of the transfer function of our plant and the controller, which is times 1 over S plus 1, okay? So we want to draw the root locus of this system. You see that based on this open loop, this loop transfer function, you see that we have a pole at -1, okay? And we have another pole at the origin because of the integrator of the PI controller, okay? And we have a 0 at minus Ki over Kp, okay? So what happens to the root locus? We can say that the closed loop poles, it starts from the open loop poles, so it starts from these poles, and they move toward together like this. They meet up here, okay? And they depart from the real axis. One of them moves along this direction, and the other one moves along this direction, okay? And then they join together here, and one of them goes to the 0, one of them goes to the infinity. Okay? So what happens if I choose a higher gain? I don't have a space to show the higher gain, so let's see the lower gain, integral gain, okay? So if I decrease ki, then we see that we have a 0 here. Okay, and in this case, the root locus would be something like this. Okay, so you see that as I increase the gain, our closed loop poles are moved further, away from the imaginary axis, and the real part would be larger, so the poles would be faster, and that's what we saw in the response of the system in the time domain, that when we increase the integral gain, our response becomes faster. But you see here that when I am on this root locus, for the closed loop on this root locus, for the higher gain, the damping ratio, for example, if I am here, you see that the damping ratio is this, is the cosine of this angle. But when I'm here, for example, for this closed loop pole, the damping ratio is this one, okay? So you see that the damping ratio decreases when we choose a higher gain, okay? And when the damping ratio decreases, it means that the system has a tendency to oscillate, and it starts oscillating, okay? Right? So. Okay, what happens to the steady state error of the system? How can we compute it? You see from the last lecture that here the type of our system is 1 because of one integrator in the loop transfer function, and so the steady state error becomes 0. Okay, for every value of the integral gain, regardless of k. Okay. So, what happens on the body plot of the system? Okay. Before studying the body plot of the loop transfer function of the whole plant, the whole system, let's look at the body plot of the PI controller. What was the body form? It was Ki times Kp over Ki S plus 1 over S. Okay? So, what is the magnitude plot? You see that we are coming from the left at a slope of minus 90 degrees because of the integrator. Okay? Something like this. And then at the 0, at minus Ki over Kp, okay, we have a flat line because of the effect of the 0, right? What about the phase? You see that we start from minus 90 degrees, okay? And then because of the integrator, and then we converge, we go to 0, 1 decade after our zero. Okay. So if you look at the body, and this is the body diagram. This one is the body diagram in the figure, the body diagram of the loop, the whole loop transfer function, the body diagram of the product of the plant and the PI controller, okay? So you see here that as I increase the gain, this is for Ki equals to 2, 5, 10, and 50. As I increase the gain, you see that the crossover frequency, which is the intersection of the magnitude plot with the 0 dB line, it's the 0 dB line. And so these are the crossover frequencies. The crossover frequencies increases. So why is the crossover frequency important for us? To compute the phase margin. And why is the phase margin important for us? Because we want to see if our system is robustly stable or not. So we are interested in larger phase margin. And we can conclude that our system in this case is more stable, okay? So we compute the phase at a frequency of, at a crossover frequency, and then the difference between the phase and minus 180 degrees would be the phase margin. So these are the phase margin, and you can see that as I increase the integral gain, our phase margin decreases, and it means that the damping ratio of our system decreases here, okay? But the crossover frequency increases, and it shows that the system, the bandwidth of the system increases, would become larger, and it means that our system would be more responsive. It is good in some sense, but it means that the sensitivity to the noise may increases. But in this case, you can see that only the low frequency gain increases as I choose the higher integral gain. Okay? This is the low frequency gain. Okay? And it increases. And for the high frequency gain, you see that it remains unchanged for different values, for whatever values of the integral gain. Okay? Why does it happen? Because if we look at the body plot of the PI controller, you see that it has a large gain for the low frequency, and it is added to the magnitude of the transfer function of our plant. But in high frequencies, its contribution is a flat line, and it acts as just as a normal gain. So it is not different, whatever value of the Ki. And so we can say that for the PI controller, the sensitivity to noise remains unchanged for different values of the integral gain. Okay? So we looked at, so far we looked at the proportional control, and moreover, we looked at the proportional integral control, the PI controller, and we say that we introduce a PI controller to have a zero steady state error, okay? But at the same time, you see that the system would be close to instability. because we can say that the PI controller adds a phase lag to our system, adds a phase lag of 90 degrees to our system. And so it decreases the phase margins, and it makes our system closer to be unstable. Okay, so this is a bad thing. And we want to balance these two things. We want to have a zero steady state error while we have a more stable plant, okay? So in order to solve it, we want to introduce another control actions, which is the derivative control action, okay? But before that, we want to consider the proportional control again for a higher order plant. In the former example, we just considered a plant of first order, which was a very simple plant. But now we want to analyze a plant of a higher order. And for this example, we consider a plant of second order, okay? So here you can see that as I increase the proportional gain, again, the response of the system becomes faster. Again, the sensitivity to noise increases. And the steady state error of the system would be smaller and smaller as we choose higher proportional gain, okay? But something different that we see here is that if we choose higher proportional gain here for our second order plant, you see that the closed loop system becomes more oscillatory. You can see lots of oscillation here for Kp equals to 50, okay? And as I mentioned before, this is a warning, and this means that your system gets close to be unstable. And that's not the thing that we want, okay? So how we can interpret, how we can justify the existence of these oscillations here for the higher proportional gain? We can say here that, for example, when we are, this is the reference signal, okay, with a unit value. And when I am here, I want to be close to the reference signal, to my objective. But when we choose a high gain for our proportional controller, it means that we are kind of overcompensating, and we make a large control action here, okay? So I become close to the objective very fast, okay? Very fast, and so fast that I pass it. I wanted to reach it, but I was too fast, and I was so fast that I passed it. I cross it, and after a while, I noticed that, I passed my objective, and then I decide to return to it, okay? And this causes the oscillations in our response, okay? So what is the solution here? We should make my response, we should make my output signal slow down here when we are becoming close to our objective, okay, right? So how we can do that? We can do that by caring about the rate of change, so that if the rate of change of the error is reducing, and we can say that E dot is negative, the derivative is negative here, the derivative of the error is negative here, then we can add this term to our drive, to our input control signal, to make it smaller, and so that it can make our speed slow down, okay? What about the proportional gain here? You see that for the second order system, the loop transfer function is k over S2 plus 2S plus 2. And so we have two open loop poles, which are still stable. They are in the left half plane. And so the root locus of our system would be something like this. As I increase the proportional gain, one of my closed loop pole moves along this line, moves up, and one of them moves down. Okay? So still you see that the closed loop poles are in the left half plane for whatever value of the proportional gain. But the thing that you should notice is that when I increase my gain, the damping ratio would decrease. Okay? So it means that our system is close to be unstable, and our system starts oscillating. Okay? And what about the steady state error? The steady state error can be computed, as we discussed before, by this formula, and it would be 1 over 1 plus k. And you can see that the loop transfer function is of type 0. We don't have an integrator in our loop transfer function. So our steady state error cannot be 0. And you can see that it is a finite value. It can become smaller and smaller by choosing a higher proportional gain, but it cannot get to 0. Okay? What about the body plots? You see that for higher gain, we just move the magnitude plot of our plant up, upper and upper. But the phase plot doesn't have any change. Okay, and you see that the crossover frequency increases, the intersection of the magnitude plot with the 0 dB line. You see that it increases. Okay, and the phase margin, which is the difference from the phase of our system at the crossover frequency to minus 180 degrees, you can see the phase margin decreases here, okay? And for the case of the first order plant, the phase of our plant, if you have a first order plant like 1 over S plus 1, you know that the phase would start from 0 and goes to minus 19. Okay, and so when I move along the phase plot, and I choose different crossover frequencies along the phase plot, the difference from these points to the negative 180 degrees would be more than 90. Okay, for all of these cases for the first order plant. But here we have a second order plant, and you see that for the second order plant, the phase converts to minus 180 eventually, okay? So as I move along the phase plot, when my crossover frequency increases, then our phase margin can become very small, and so it can become close to 0, okay? So it is a danger, it is a warning for our system. And it shows that our system would not further be robustly stable, okay? But you can see that both the high frequency and the low frequency increase when I choose a higher proportional gain. So, okay, so as I mentioned before, When we look at a derivative control, we kind of have a preview of what our error signal will do in the near future, and we can have a prediction of the behavior of our error. So when we are closing to our objective and we are too fast, we add a term to our control input, to our drive to the plant, so that it make it slow down, okay? So this is the effect of a derivative control. So now we introduce a PD controller, a proportional differential controller. We look at the error, we multiply it by a proportional gain, and then we look at the error, we take it and derivative it, and multiply it by some derivative gain. This is Kp and this is Kd. Okay. So the control input in the time domain can have this form. It can be represented by Kp times the error plus the derivative gain times the derivative of the error signal, okay? So the derivative action, we can say that it acts like a brake, okay? And so if the error of the system is reducing, and so the rate of the change, the derivative is negative, it adds a negative term to the control input, and so it decreases, okay? And so it is some kind of brake in our system, okay? But notice that the transfer function in the frequency domain can be represented by Kp plus Kds, okay? We have two subsystems in parallel, a proportional transfer function, and you remember that the transfer function of a differentiator is S, and so the transfer function of our controller, this is the PD controller, would be Kp plus Kds, okay? But notice that this is not a proper transfer function. Why? Because its nominator, which is Kp plus Kds, is first order, but its denominator is 1, which is 0 order. So the degree of the nominator is greater than the degree of the denominator, and so this system is improper. And so it is not realizable. It is not causal. And we cannot implement it physically, okay? So if you want to implement this transfer function, a PD controller for our system, we should approximate it by adding some poles which is very fast, so that its effect on the transfer function is very low. So we add some terms as Kp plus Kds over Cs plus 1. And if we want to have this pole fast, we should choose a small constant c, okay? So for now, don't worry about the implementation, and we think that we can implement it as Kp plus Kds, okay? So here, we see that what happens to the response of the system in the time domain, and we see that as the derivative gain increases, this is for, we keep the proportional gain to 50, okay? This is for Kd equals to 2, Kd equals to 5, the yellow one is 10, and this is one. This one is 50. Okay. we chose a high proportional gain here so that the steady state error of our system would be small, okay? Which we set it to 50, okay? And then we change the value of the derivative gain, okay? And we see that as the derivative gain increases, you see that the steady state error is not affected. Why? Why with a derivative control, the steady state error cannot be affected? Because at the steady state, we see that the derivative would be zero, right? Okay? The derivative of our response at a steady state would be zero. Okay? We don't have any change at a steady state. And this is the meaning of the steady state. So the derivative is zero in here. And so the derivative term cannot affect the steady state error. And moreover, you see that the response of the system would become more slower, okay, but becomes less oscillatory. And so it means that the damping ratio of our system increases, okay? And at the same time, one of the bad effects of the PD controller is that the sensitivity to noise increases, okay? And you can see it by looking at the response of the system in the time domain. So look at the same thing from another viewpoint. Look at what happens under root locus. You see here that okay, what is the loop transfer function here? This is Kp plus Kds over S2 plus 2S plus 1, okay? So we see that we have two open loop poles and a 0 at minus Kp over Kd, okay? So our root locus would be something like this. We start from the open loop poles, and one of our closed loop poles moves in this direction. The other one moves in this direction. And one of them goes to the 0, to the open loop 0, and the other one goes to infinity. Okay? So, you see that as I increase Kp, as I increase Kd, which is the derivative gain, you see that the 0 of the system moves to right. And so this would be the root locus of the new system, okay? And you can see that the damping ratio of the closed loop pole here would be larger, okay? Compared to the damping ratio of the closed loop pole on the root locus for a less value of derivative gain, okay? So it means that our PD controller adds some damping to our system. It increases the damping ratio of our system, and so our system becomes more stable, and the oscillations becomes less. Okay, what about the body diagram? We can see, we can look at the plot of the PD controller first. Kp plus Kds. So we start with a flat line, and at minus Kp plus K over Kd, we go up at a slope of 20 dBs per decade. What about the phase? We start from 0 degrees, and then we go up to get to 90 degrees, okay? Right? So you see that in low frequencies, by changing the derivative gain, we don't have any change in the magnitude plot of our system. So for different values of the K, for whatever values of the KD, the derivative gain, the low frequency gains does not change, okay? But for the high frequency gains, we see that we increase them because we add them with by this line, and so we can say that the high frequency gain increases when we choose a higher value for the derivative gain. Okay. So it means that the sensitivity to noise increases for this controller. This is the bad side effect of this controller. This is the disadvantage of this controller. That it is make our system more sensitive to noise. But you can see that the crossover frequency increases. It means that the system would be more informative. The bandwidth of the system would be larger. And you see that the phase margin of the system here, you can see that the phase margin increases, okay? And this is because of the phase that the PD controller adds to our system. And we can say that it adds a phase lead of 90 degrees to our plant. And so it makes our plant more stable. It increases the phase margin, okay? So now, so far, we looked at proportional control, derivative control, and integral control. And we talked about the advantages and the disadvantages of any of these controllers. Now we can put the three components together with a PID control, okay? We can have only a proportional controller in our plant. We can have only a proportional integral controller in our plant, or we can have only a proportional derivative controller in our plant. Both of these three controllers are used in industry for controlling the processes and the plants, okay? But we can have the benefits of the three components, the three controllers, and introduce a PID controller, okay? So this is the block diagram of the PID controller. It can be represented by this diagram. And so we can say that the control input can be represented by this formula. We look at the error. We can multiply it by a proportional gain. We look at the error and we can integrate it and multiply by an integral gain. And then we can look at the derivative of the error and multiply it by a derivative gain and add them together. These are some components in parallel. So for computing the transfer function of a PID, we add these transfer functions of every subsystem together. So this is the transfer function of our PID controller, okay? Kp plus Ki over S plus Kds, okay? So it can be rewritten as this form. We can write it as Kd. Let me a few seconds to conclude this slide. We can write it as Kd times S squared plus Kps plus Ki. So the denominator of this transfer function is a second order polynomial. And the factor multiplies by the S squared term is the derivative gain. The factor multiplies by the S1 term is the proportional gain, and the factor multiplies the zero order term is the integral term, okay? And you can see here that this transfer function is not causal, it's not proper. And so we should, in order to implement the PID controller, we should approximate it by adding some poles. And we can add some poles, some fast poles like CS+1 here. Okay, let's continue next week.